Good day, everyone. Our topic for today is on volcanoes. For this lecture, there are two parts, part 1 and part 2. And for this video, part 1 will be given. I'm Dr. Sandra G. Katane. I'm your lecturer and teacher for this topic. Volcanoes of the world. Volcanoes are formed along plate boundaries. Plate boundaries meaning convergent plate boundaries, divergent plate boundaries, and transform fault boundaries. But volcanoes are just concentrated in the first two types of boundaries, convergent and divergent plates. There are other volcanoes that are formed not along plate boundaries but in the middle of plates. For example, the volcanoes in Hawaii, we call them hotspot volcanoes. There are about 1,500 potentially active volcanoes globally, excluding the continuous belts of volcanoes in the ocean floor and mid-oceanic ridges. There are about 500 of the 1,500 volcanoes erupted in historical time. Plate tectonics and volcanism. We will explore here the relationship of volcanism and plate tectonics. Volcanoes form when tectonic plates collide and one plate is pushed beneath the other. This area is called convergent plate boundary. Partial melting occurs when water from the subducted ocean sediment lowers the melting temperature of the mantle, giving rise to melt. When tectonic plates move away from another to produce volcanoes, this is called the divergent plate boundary. Decompression occurs when confining pressure is released due to plate separation. Hot magma rises from the mantle at the mid-oceanic ridges, pushing the plates apart. This molten rock then rises to the surface and erupts in volcanoes. In the middle of the plates, some areas of the mantle are anomalously of high temperature to cause melting. The volcanoes associated with these settings are called hotspots or simply called hotspot activity. Some of the voluminous eruptions were formed from hotspot volcanoes. For example, the Deccan traps associated with the extinction of dinosaurs, which occurred at the same time. And the other one is the Siberian traps found in Siberia. These are large volcanic provinces associated with hotspot volcanoes. This is the model for Hawaiian volcanism. It's the most famous hotspot in the world. The plates move on top of a stationary magma source. A famous example of hotspot volcanoes in Hawaii are those that form the chain of islands. It is the north-trending volcanic chain that can be traced from the Emperor Seamount chain, where volcanoes increase in age, like what is shown here. The youngest of the volcanic islands in Hawaii is the Big Island, and as you move to the northwest direction, the age of the volcanoes or volcanic islands increases. And it continues to the seafloor or Emperor Seamount chain to the northwest. Virtually, this stationary hotspot source supplies magma to the volcanoes along the chain. As you can see, in Hawaii, the alignment of the volcanoes also records the change in direction of the motion of the Pacific Plate. This table shows a list of selected historic volcanic events. The impact of the modern eruptions are given in this column. It shows the number of casualties and the effects of the eruptions. However, the eruptions can be compared not on the number of casualties, but more on the amount of magma released in a single eruption episode. For example, the 1815 Tambora eruption in Sunda Arc, Indonesia is the largest recorded in human history and the largest during the Holocene, with roughly 180 cubic kilometers of magma released within days during the 3 months eruptive phase. But in this list, you can see huge numbers, like the one in Krakatau, Indonesia. This is another famous eruption. It's related to 36,000 deaths. In Italy, we have 16,000 people who died. And we have also some eruptions with equally similar number of deaths, like in Nevado del Ruiz in Colombia, 22,000 people. There's even an activity in La Sofia in St. Vincent, which killed 2,000 people, and it's also caused the extinction of the Caribbean Indians. What causes volcanic eruptions? Although there are several factors, internal and external factors that are triggering volcanic activity, the most important causes of volcanic eruption is buoyancy of the magma, the pressure from the exhaled gases. We also describe it as vesiculation or degassing of magma, and the injection or influx of fresh magma supply. The other factors may be contributory, but we have the three factors that are dominant. And I think the most important reason is vesiculation or degassing of magma, which allows the escape of magma from the melt, and this is the most important cause of volcanic eruption. What comes out from a volcano? Lava, pyroclast, volcanic gases. Lava is a molten rock coming from the magma. We call it lava only when it surfaces, when they are extruded on the surface. Lava is normally made up of crystals, volcanic glass, and bubbles or gases. But in general, we have the lava, which is a coherent magma. We have also the fragmented magma called pyroclast, or sometimes you call it as tephra, or fragmental magma, fragmental lava. And then we have volcanic gases. Chemically, the gases are made up of silicon, oxygen, aluminum, iron, magnesium, potassium, phosphorus, titanium, plus other small elements, other elements in small concentrations. Pyroclast or tephra is any volcanic fragment that's ejected through air by volcanic process. It's a pyroclastic eruption is one in which the great majority of activity involves fountaining or explosions. Example of pyroclast is Spamis. Pyroclastic rocks are clastic sedimentary rocks composed solely of primary volcanic material. An erupting volcano will increase gases, release gases, lava, tephra, and heat into the atmosphere. When gases are dissolved in a magma, they are called volatiles. This slide shows the 2000 eruption of Mayon volcano when it formed a lava flow at the southeastern flank. The surface of the lava flow is fragmental, and this is quite common, but the interior is normally coherent. When this lava was being erupted, this is what you see at night. You can see the glowing side or glowing flow at the side of the volcano. Eruption products. Pyroclast, derived from the Greek terms meaning fire and broken. These mainly are derived from explosive eruption. So these are examples of pyroclasts. They occur in different sizes, such as volcanic bombs, can be as large as a car or a house. It can be lapilli size, and volcanic ash like this can be very fine as clay and sand. Ash is a fine dust of volcanic rock. Pumice, like this, is a type of pyroclast. It is produced when lava with very high water content is discharged from a volcano. When this pyroclast cools and hardens, the result is a very light rock filled with tiny bubbles of gas. Pyroclasts are mainly derived from eruption column of the volcano. This includes also the ballistics near the crater and the pyroclastic flows here. This is where you get most of your pyroclast. Pyroclastic flows and deposits of Mayon 2001 eruption. These massive beds here are separated by discontinuous ash, lapilli fallout, but these are products of individual flows. The entire section is around 4 to 5 meters high. The process that produced this deposit, this chaotic deposit, is a pyroclastic flow, and this is how it looks like when it is when you see the process itself. When these rocks become consolidated, they are called pyroclastic rock. When they become rocks, they are no longer friable. They are hard, they are consolidated, and they can form blocks. The principal components of volcanic gases are water. This is the most abundant, water vapor. Next is CO2, followed by H2S, nitrogen, argon, helium, methane, carbon monoxide, and hydrogen. The most toxic among them is the hydrogen sulfide, H2S, which can be fatal when inhaled in large quantities. Volcanoes can silently release these gases unaccompanied by magmatic eruption. So there are some cases when Taal volcano erupted in its history without undergoing explosive activity. Carbon dioxide was released silently without any accompanying eruption. Types of volcanic eruptions. There are two types of eruption in terms of activity: explosive eruptions and effusive eruptions. Explosive eruptions are characterized by gas-driven explosions that propels magma and tephra. Example of this type of eruption is the 1991 eruption of Mount Pinatubo. Mount Pinatubo is situated in central Luzon. Effusive eruptions, meanwhile, are characterized by the outpouring of lava without significant explosive activity. An example of this type of eruption is the eruptions of Kilauea volcano in Hawaii. Traditionally, the types of volcanic eruptions were adapted mainly from the name of volcanoes where the processes were initially observed. For example, Hawaiian, it was observed in Hawaiian volcanoes. Strombolian was observed in the Stromboli Island in Italy. Vulcanian from an island in Italy called Vulcan. And another one, Vesuvian, is also from Vesuvius volcano in Italy. Other types are based on the mode of mechanism of eruption, whether phreatic, phreatomagmatic, Plinian eruption. The term was named after Pliny the Younger. Pliny the Younger is the one who described in 79 AD eruption of Mount Vesuvius, which destroyed the ancient Roman cities of Herculaneum and Pompeii. Because of the descriptive manner of the classification, volcanologists around the world, especially during the 1980s, found it more convenient to classify them into two main types, explosive and effusive. The traditional names may be reclassified under these two main types. Classification schemes were subsequently based on quantitative data, including eruption column height and dispersion of tephra. In 1982, Newhall and Self introduced the scale, we call it the Volcano Explosivity Index, or VEI, to classify volcanic eruptions. This is the eruption cloud or plume of the 1991 Pinatubo eruption. The eruption on June 15, 1991 was of Plinian type. Plinian eruption is the most explosive among the types, in which a stream, gas, and ash is violently ejected over 25 kilometers above the crater of the volcano. This is the 91 eruption of Mount Pinatubo, and it is the peak of the eruption. It occurred in June 15 at 1631 hours. The diameter of the plume is roughly 600 kilometers across. And this what you see now is a plan view of that eruption. So the plume was bigger than Luzon Island itself. Calderas. Caldera, we mentioned about Plinian eruption in the previous slide. Caldera is a product of Plinian eruptions. Plinian eruptions are often associated in their formation. Calderas are the largest volcanic landform on Earth. By definition, caldera is a large depression formed by the collapse of a wide area due to the emptying of the magma chamber in a short period of time, can be days to weeks, a result of large volcanic eruption. In this slide, you can show how a caldera is formed. Initially, we have a regular or normal volcano erupting. It can be from a single vent, can also be from several vents. Because of the high rapid rate of magma extrusion, underneath the land, it becomes unstable because there's a lot of magma drawn out from the volcano and it caused the area to collapse. The geomorphological feature that is formed after the collapse is called the caldera. Examples of caldera are Laguna and Taal calderas. We have here Taal caldera, Taal volcano, which erupted in January this year, has a caldera. It means that the volcano at the center is just part of the volcanic system of Taal. The caldera is the bigger crater where Taal Lake is nested. You can view the caldera if you are standing along the rim of caldera, especially in Tagaytay City. You can also view Taal volcano. The other example of caldera is Laguna, but it is not well studied as Taal, and only the middle lobe of Laguna Lake is being claimed as a caldera. But in terms of age, Laguna caldera is much older than Taal caldera. The latest caldera activity of Taal is 5,000 years ago. Huge rhyolitic eruptions. There are many large eruptions in modern history, but the largest volcanic eruptions were not observed by humans. Volcanoes can be classified based on the volume of magma released, as we discussed earlier. The 1991 Pinatubo eruption was very large in the classification, or we call it as VEI, or Volcano Explosivity Index. It is classified from between 5 to 6, but it's being classified as very large eruption. And magma output of that eruption is roughly 6 cubic kilometers. But the Long Valley caldera eruption, which in about 760,000 years ago, it produced a magma with a volume of 600 cubic kilometers. And there's another one from Yellowstone caldera. Its eruption was 600,000 years ago. The volume is almost 3 times of Long Valley caldera, estimated at 2,000 cubic kilometers. If you compare the volume of eruption of the Mount Pinatubo with those that happened but not observed in Long Valley caldera and Yellowstone, we can consider that Mount Pinatubo eruption in 1991 is not enormous, but it was the third largest eruption in the last century. The small eruptions like the one that was produced by the eruption of Taal in January of this year could be classified as small volume or small VEI eruptions, maybe VEI 1 or 2. Volcanic hazards. So this is a list of the hazards that we can expect from a volcano. We have lava flows, tephra or ashfall, and ballistics, pyroclastic flows, and pyroclastic surges. These are also called PDCs. Volcanic gases, lahars, debris avalanches, or landslides, and tsunamis, and the last, crater lake or mountain lake breaching. We look at the hazard from lava flow. Lava flow hazard is mainly by burial. Burial by lava flows render the land useless for decades. The US government turned the hazard to an opportunity in the Big Island of Hawaii by developing tourism. Eruptions in the Big Island also provided additional land and space for the country and for the residents. Pyroclastic flows and pyroclastic surge, or we call them as PDCs, pyroclastic density currents. They are dubbed as killers. They are the most dangerous process related to volcanic eruption. They contain hot solid, sometimes liquid, solid materials in gas dispersion. They are, of course, classified as density currents, and the main hazard is via burial and erosion. A pyroclastic flow is fast-moving current of hot gas and volcanic matter, collectively known as tephra, that flows along the ground away from the volcano at high velocities of 100 kilometers per hour. Actually, that's an average, but it's capable of reaching speeds up to 700 kilometers per hour. Imagine that if you're driving at 100 kilometers per hour, That's just the average speed of a pyroclastic flow. You really have to beat the 700 or even 1,000 kilometers per hour. So basically, if you are situated along the path of a pyroclastic flow, it could be very dangerous and very hard to survive when pyroclastic flows flow down along the slope of the volcano into your site or location. The downstream directed billowing cloud in the photo is we call the pyroclastic flow. This is the eruption plume of the eruption. This is again an image of the pyroclastic flows of Mayon volcano in 2001. The flows flowed along the streams on the slopes of the volcano, mostly at the southeastern side. The pyroclastic flows are fed by glowing and collapsing pyroclast-laden columns at the summit or at the crater. You can see in this photo at night, you can see the path of pyroclast ejected at the summit region. But during the day, you cannot see the eruption on top of the volcano, but you can see the descending pyroclastic flows. This is a close-up view of one of the pyroclastic flows of the 2001 eruption. Saint Pierre, Martinique, Mount Pelée eruption in 1902. These photos here are before and after. The town of Martinique is a progressive town. The volcano is at the background, you can see here. And this is after the 1902 eruption. Mount Pelée eruption in 1902 destroyed the town of Saint-Pierre, or we call it as Martinique, killing about 30,000 people in the space of few minutes in the worst volcanic disaster of the 20th century. Augusto Sibari was the only person who survived this eruption. He was a prisoner kept in a dungeon. He sustained third-degree burns, but he survived the eruption. Next hazard, tephra fall or ash fall. Tephra fall or ash fall can cause collapse of roofs when they accumulate on these structures during an eruption. It can cause crop damage. It can be an eye irritant, but it is a serious cause of respiratory problems. Ash and hazard to aviation. This is a plane that was parked in the former Clark Air Base in Pampanga during the 1991 Pinatubo eruption. It sat on its tail due to the weight of the ash. Ash, when wet, can increase its weight 3 times. Ash normally collects on the roofs, which render the collapse of structures. But the most serious hazard from ash falls is related to aviation. When an aircraft flies into an eruption cloud or in the atmosphere and drained with ash, normally where the concentration of ash is low, it is not immediately visible to the pilot. Ash, when ingested, can damage aircraft engines, or worse, can cause engine failure mid-air. The eruption of a volcano in Iceland in 2010 occurred beneath glacial ice, and it produced a lot of ash. Ash was then carried over the downwind to Europe into some of the busiest airspace in the world. In response to concerns that volcanic ash ejected during the 2010 eruptions of this volcano in Iceland would damage aircraft engines, The controlled airspace of many European countries was closed to instrument flight controls traffic, resulting in what at the time was the largest air traffic shutdown in Europe since World War II. As many as 16,000 flights of the daily 19,000 flights were canceled by 21 April 2010, and a total of 95,000 flights have been canceled across Europe during the 6-day airspace ban. Global cooling. The Pinatubo eruption in 1991 produced colorful sunsets due to the reflection of light when ash particles were bombarded with sunlight. Because ash particles scatter and absorb incoming sunlight, aerosol particles, including ash particles, exert a cooling effect on the Earth's surface. The 1991 Pinatubo eruption increased aerosol optical depth in the stratosphere by a factor of 10 to 100 times normal levels measured prior to the eruption. Consequently, over the next 15 months, scientists measured a drop in the average global temperature of about 1 degree Fahrenheit, or equivalent to 0.6 degrees Celsius. Next hazard is noxious gas. In this case, we use the example of the disaster in Cameroon in 1986. Cameroon is located in Africa. On August 21, 1986, a limnic eruption at Lake Nyos in northwestern Cameroon killed 1,746 people and 3,500 livestock. The eruption triggered the sudden release of about 100,000 to 300,000 tons of carbon dioxide. The gas cloud initially rose at nearly 100 kilometers per hour, then being heavier than air, it descended onto nearby villages, displacing all the air and suffocating people and livestock within 25 kilometers of the lake. So you can see in this series of pictures the impact of that eruption. There was no magmatic activity. It was just the release of carbon dioxide, but the gas eruption claimed so many lives. This is the end of Volcanoes Part 1. Thank you for watching.